Alright, good day everybody. Today I'm taking a topic called wave. Alright, I know it's a topic that we are all familiar with in physics. Alright, so some of the subtopics I'm going to be dealing with, I'm going to be giving the definition of wave, I'm going to be explaining the definition of wave, I'm going to be giving examples of wave using everyday phenomena. Alright, I'm going to be giving examples of waves using everyday phenomena. Everyday phenomena in the sense that, a wave is actually happening around us, but we just don't know that those are examples of wave. Alright, so I'm going to be giving a series of examples of wave that we are actually familiar with, but we never knew are examples of wave. Alright, so other than that, I'm going to be talking about the classes of wave and give their examples. Alright, I'm going to be giving the types of waves with their examples. I'm going to be explaining the terminologies in waves. Terminologies in the sense that words that are difficult, there are concepts that we need to understand before we will be able to grasp the whole concept of wave. And then I'm going to be solving 12 different questions, calculations on wave. I'm going to be solving 12 different questions on wave. So let's walk. Alright, so I'm going to be defining a wave for you. I'm going to be giving the definition of wave. Alright, so it is said that a wave is a disturbance or vibration which travels through a medium. Alright, so I will need you to underline disturbance or vibration. I'll need you to underline travel. I'll need you to underline medium. Alright, so I'll start over again. A wave is a disturbance or vibration which travels through a medium, transferring energy from one point to another without a permanent displacement of the medium. Alright, I'm going to repeat it again. A wave is a disturbance or vibration, alright, which travels through a medium, transferring energy from one point to another without a permanent displacement of the medium. Alright, so the key words in this definition are disturbance, alright, you have vibration, we have travel, we have a medium, alright, transferring energy, so we have transferring energy from one point to another, alright, without a permanent displacement. Alright, so I'm going to use this analogy to explain the definition. Alright, so the first analogy I'm going to be using is you have a bucket of water, alright, and you throw your stone inside the bucket of water. Alright, the bucket of water is filled with water, alright, and you're throwing a stone inside it. So when you throw a stone inside it, you will observe that ripples are being formed from the surface of the water. Alright, so let's assume that the water, alright, inside the bucket is the medium, alright, but as you throw the stone inside the water, you will observe that there's going to be a disturbance created or a vibration. Alright, so if you get a lid of a bottle of Coke that we call Cantas, if you throw it on the surface of the water that is vibrating, that is being disturbed already, you will observe that vibration, alright, will move the lid of the Coca, your Cantas. It's going to move it from one place to another. In fact, it is possible that Cantas will be eating the body of the bucket in such a way that it's going to be moving from one place to another. Alright, so I'm going to go back to this again. Alright, so a wave is a disturbance or vibration. So that disturbance or vibration is caused as a result of you throwing the stone inside the bucket and you have the water, bubbling, more like moving from one point to another. Alright, as a result of the stone that you threw inside of it. Alright, so the movement, alright, is the disturbance or the vibration. But you observe that when you put you put a plastic plate, or just like I gave the example of a Cantas, if you throw a Cantas under water, you observe that as the water is moving, as the ripples is being formed, the ripples will be carrying that Cantas, alright, from one point to the another. All right, but you will observe something. You will observe that there is this part of the definition without a permanent displacement of the medium. The medium is the water inside the bucket that is moving. All right, but do you ever observe that the water will leave inside the bucket and will spill on the floor? No, if it is partially filled. All right, so that's one of the examples or an everyday phenomena of wave that has actually been happening around us that we don't know. All right, another example is the beach, the ripples, and the surf. All right, if you've ever been to the beach before, you will observe that by and by, the ocean wave, the ocean current ensures that the water, all right, from the sea, moves towards the beach. All right. So now one of the things that might cause that is as a result of the force. All right, the force from the air. All right. So the water moves from from the sea. All right, and forms big ripples, and it moves to the surface of the beach. All right, and moves back inside. All right, so you will observe that if I'm sure you would have seen this part in movies before, where some guys will go and get some a diving board. All right, they call those guys surfers. They surf. The surf is S-U-R-F. All right, so I'm sure you would have seen it in movies. They will go get a diving board, and then they will surf. They will surf on the crest, all right, of the ocean current, and then you will see them moving. All right. So what is actually happening is that, let's say this is the ocean. Let's say this is the beach here. Let's say this is the beach here. All right. You see that the guys are having the board here. All right. So the guy is standing on this board here. All right, and he's climbing on this ripple. This is called ripple. Right, he's climbing on this ripple, which is the crest of the ripple, and then what is actually happening is that because this sea is being disturbed, it's being caused to vibrate, it will move the object that is on it. All right, because it is transferring energy from one point to another. It will move this diving board, all right, from this point and move it to the beach. All right, but it doesn't change. It does not mean that the water is going to reduce inside the sea. All right, the water level does not reduce because it always goes back to where it comes from. So you will observe that those are everyday phenomena or instances. All right, where wave is being applied. So I'll go back to the definition again. A wave is a disturbance or vibration which travels through a medium. All right, the medium could be water. All right, transferring energy from one point to another without a permanent displacement of the medium. So in that bucket, you will observe that the water is not leaving the bucket, but it's just that because it's being disturbed, it is transferring energy and causing the counters to move on the surface of the water. All right, same thing with the beach. It is not that the sea is completely going to get dry at the end of the day, but we observed one thing: there is always a transfer of energy. The energy is being applied on this person that is on the board, all right, and then the energy pushes the man and the diving board, the surfing board, and moves him to the beach. All right, so this is the definition and some examples of wave that we've actually been experiencing, but we don't know that they are examples of wave, and we don't know that we're actually experiencing wave. All right, this morning I was sitting in my house, and from afar I could see the tree. You know, the wind was pushing the tree so much that the tree was vibrating. You know, while it was vibrating, there was a sound being created by the movement of the tree, more like a whoosh sound, and so that could be an example. Also, that could be an example of wave. All right. So the wind is coming as a form of force on the tree, and then there is a vibration of the tree, all right, and then there is an energy being created, an energy which is being converted, all right, to sound energy. So so I think with this you should be able to get the definition of wave and the examples of wave. All right, thank you. All right, good day everyone. So this is a class, a continuation on wave, the class we started yesterday. So today I'm going to be talking about the terminologies in wave. All right, first I'm going to be starting with amplitude. All right, so but I will have to use this diagram to explain the concept so that everyone can understand very well. So I hope you see the board clearly. So I have my displacement here. So I have a sinusoidal wave graph. So this is a function of x and time. So here I want to try to explain amplitude with this, alright? So let's say that as a result of the disturbance, alright, on our graph, we might either have a displacement of this sort. Probably, let me try to draw it again. Probably something of this kind. Then probably something like this. Then this should be enough. Alright, so let's say I have here, I have 0, I have here, I have 1, I have 2 here, I have 3, and then I have 3 here, and then here y, I have 4 here, I have 4 here, and then 5 here. Alright, so if you trace this up, alright, this is the maximum displacement here. Alright, tracing it to the y-axis, alright, this is maximum displacement is 5 meter. Alright, the y-axis is in 5 meter. Alright, but this is in at 2 meter. Alright, it has a displacement of a magnitude of 2 meter. Alright, but if you were to check this, probably this is going to be in 3. Alright, if we should check this, this most likely might be in 3 at 3 meters. So that means that amplitude is defined as the displacement, alright, of your of the particle, alright, that has the maximum displacement. Right, so here the one that has the maximum displacement here is let's say this is A, B, and this is C. So the one that has the maximum displacement is B, alright, because it has 5 meters. Followed by this one, C, particle C, that has 3 meters, has a displacement of 3 meters, and particle A that has a displacement of 2 meters. So the amplitude is defined as the maximum displacement of the particles of the wave from its main point or in equilibrium position. Alright, so amplitude is defined as the maximum displacement, displacement of the particle of a wave, alright, from its mean or equilibrium position. Alright, and it has a unit. The unit is meter, but if you have it in centimeter, you can convert it back to meter. All you just need to do is divide it by 100. Alright, so that's that for amplitude. most times it is the y-axis is always in meter, all right, but your x-axis could also be a function of time, all right. So this could be probably like 2 seconds, the 2, this could be 4, this could be 6, this could be 8, this could be 10, and this could be 12. So if they said they might ask you a question and they might say that at what time do you have your maximum displacement? All right, at what time do you have your maximum displacement? All right, so and that should take place here. All right, here, which is at 0.5 seconds. Which is at 0.5 seconds. Which is at 0.5 seconds. So I go straight away to the next terminology, all right, which is wavelength. But I will also have to use this diagram to explain wavelength. All right, so let's say, all right, let me try to draw another diagram. Let's say I have my x, t here, and then I have my y here, the displacement in meters here, all right, and then so I have my waveform here. All right, so from this point to this point is a complete cycle. From this point to this point is one cycle. All right, so for one cycle, all right, you have one wavelength there, and a wavelength is represented by this symbol lambda. It's called lambda, lambda. All right, so from this point to this point is one complete cycle, and that is your one wavelength. All right, but also there is this point here, and there is this point here. There's also this point here, and there's also this point here. So this point we call it crest. All right, this is another crest here. All right, but the crest is most times the place where you have your maximum displacement. All right, so but at this point here you have your trough. It's called your trough, T-R-O-U-G-H. Same thing with this place, you have your trough, T-R-O-U-G-H. All right, so it is said that the distance, successive distance between two crests, all right, is also one wavelength. The successive distance between two crests, all right, is also called one wavelength. The distance between two successive crests or two successive troughs. All right, so this place and this place can also be your one lambda. All right, so but it is possible for you to have 1/2 of a lambda. It's possible for you to have 1/4 of a lambda. It's possible for you to have 3/4 of a lambda. So let me try to explain that for you. So from this point here to this point here, all right, you know we said that from here to here is one wavelength, right? So that means that from this point to this point, which is the middle of the whole cycle, is your 1/2 wavelength. So this is half of a wavelength. All right, so and at this point here we have a node taking place here. All right, so this place too is 1/2 of a wavelength. All right, but I can find the half of a wavelength. All right, the half of a wavelength. So if this place to this place is half a wavelength, this place to this place is half a wavelength, this place also is half a wavelength, and this place also is half a wavelength, but I can find the half of it. All right, so that's going to be, I divide this by 2. So if I divide this into 2, that means that it's going to be lambda over 2 divided by 2, which is going to be lambda over 2 times 1/2, which is going to be lambda over 4. All right, so that's going to be lambda over 4. So that means this part here is lambda over 4. Same thing with this side is lambda over 4. So if you add lambda over 4 plus lambda over 4 together, you're going to get lambda over 2. All right, so that's that for a wavelength, and then it is measured in meter. All right, it's measured in meter. So some other people define it as the distance covered by a wave when it completes one cycle. The distance covered by a wave when it completes one cycle, in the sense that from this crest to this other crest is one complete cycle. So from this trough to another trough is one complete cycle. So from here, from this trough, rather to this point here is a wavelength. From here to this point here is a wavelength. From here to this point here is a wavelength. From here to this point here is a wavelength. Alright, so that's that for a wavelength. And just like I said, the unit of the wavelength is meters. Right, but if you have it in kilometer or you have it in centimeter, you can always convert it to meter. To convert it from centimeter to meter, you just have to divide by 100. Alright, but if you want to convert from kilometer to meter, you just have to multiply it by 10 raised to the power 3, which is 1000. Alright, I'll go straight to the next one, which is the period. Alright, the period. Alright, so the period is the time taken to make one complete oscillation. Alright, or to make one complete cycle. The time taken to make one complete cycle. So if you move from here, alright, down to this place, as you're moving, you know you're moving in time, alright, with time. So we can say that from here to here, you covered the wave covered, the particle covered the time 2 seconds, alright. So if this side is 2 seconds, that means that to this side too is 2 seconds. So meaning that this place is going to be 4 and this is going to be 2, alright. So this is going to be the half is going to be 1, 2, 3, and 4 seconds. So the time taken by a particle of a wave to perform one complete cycle or oscillation is defined as the period. Alright, so another formula that I'm going to give to you, alright, the period is represented by T. Alright, so the period T is represented by T, alright. Don't forget I said it is the time taken, alright. It is the time taken to make one complete oscillation. Alright, so there is another formula. So it is time taken, T equals to time taken divided by the number of cycles. Alright, time taken divided by the number of cycles. Alright, so that's that, and it is measured in seconds. It is measured in seconds. So I'm going to, or you can also say that the period is time taken divided by number of wavelengths. So I can explain how you can get the number of wavelengths for you. That's very simple. Alright, let's assume I want to go back to the diagram that I drew for you the first time. Alright, so let's assume I have this. Alright, let's assume I have this. This is my x or t, and then this is my y. This is the displacement of my particle. Alright, so from here to here is one wavelength. From here to here, of course, sure you know that that one too is one wavelength. Alright, so that's how you can determine the number of your wavelength. Alright, so from here to here is one wavelength, and then from here to here is another wavelength. So that's how to determine the number of your wavelength. So your time taken would have been specified here. Probably here is 1, probably 0, 1, 2, 3, and then 4 is here. So if you were to find the period, alright, the time taken for this complete oscillation is 2 seconds here. For just one complete cycle or one complete oscillation is 2 seconds here. So I go straight to the next next terminology, which is the frequency. Alright, so the frequency is actually the reciprocal or the inverse of your period. Alright, your frequency is the number of cycles divided by the time taken. You know your period is time taken divided by the number of wavelengths, or your period is time taken divided by the number of cycles. So, but your frequency is the opposite. Alright, so it's going to be the number of cycles. I'm sure you sure will be able to guess that. So your frequency is going to be the number of cycles formed by the wave all right, divided by the time taken, all right, which is going to be n over t, all right. But for your period is t divided by n, all right. So if I want to use this other formula, it's going to be my frequency, all right, frequency equals to the number of wavelengths, which is still the same thing as number of cycles. Don't forget, your wavelength is still the same thing as number of cycles, divided by what? The time taken. Alright, so that's done. And then so your frequency is the number of cycle or oscillation which the wave completes in 1 second. Alright, so and then the unit of your frequency is hertz. H-E-R-T-Z. It's represented by Hz. Alright, the unit of your frequency is hertz. It's represented by Hz from the scientist Frank Hertz. Alright, so that's that. And then also don't forget I said that your frequency is the reciprocal of your period. So also your period is the reciprocal of your frequency. So that means that there is a link, there's an equation between period and f. So that means that your t is your 1 over f, and your f is also your inverse of your t. So your f can be 1 over t, and your t could be 1 over f. Alright, so then I go straight to the last one that I'm going to be talking about, which is the wave speed or the wave velocity. Alright, the wave speed or the wave velocity. Alright, so and then I'm sure you're familiar with speed in physics. Alright, speed, more like how fast a body is moving. So of course you should know that the wave the movement of the particle, all right, just like a vehicle can move very fast and at the same time move very slow, and can decide to move very slow, same with the wave. The particle of the wave could either be moving very fast or moving very slow. All right, so the formula for wave speed or wave velocity. Alright, I'm sure you know the formula for the speed. Speed in physics is distance over time. Alright, so if this speed is distance over time, that means that our wave speed is equals to the wave distance. Alright, wave distance divided by the wave time. Alright, the wave speed is equals to the wave distance divided by the wave time. And the letter we use to represent our wave speed is V equals to the wave distance is our lambda, alright, which is the wavelength. Alright, don't forget that we said wavelength is the distance between two successive crests or two successive trough. Alright, the trough is TROUGH, don't forget. So, which is our lambda, divided by the wave time is the period. To make one complete cycle, alright, the time taken to make one complete cycle or one complete revolution. Alright, so but don't forget, I can transform this formula in the sense that, you know, I told you that T is equal to 1 over F. Alright, so I can say that my F equals to 1 over T. So I can substitute this formula here, and then I have my V is equal to lambda times 1 over T, and my 1 over T is what? Is F. Don't forget, my F is 1 over T, so I'll just substitute this here, and then I have my lambda times F. Since my F is 1 over T, it's going to be my V, so my V is equals to, my wave speed is going to be the wavelength times the frequency. Alright, so there are two formulas now for the wave speed. It is either V equals to lambda over T, or it is lambda F. So either wavelength divided by the period or the wavelength times the frequency, which has a unit of hertz. Alright, so I'm going to continue by solving. You know, I promised you in the last class that I'm going to be solving close to 12 questions for you. Alright, so so I'm going to be solving the question for you, the 12 questions for you in the next video. Really, thank you very much for your time.